Everything described so far has a conventional explanation. The magnetic poles move because of fluid dynamics in the outer core. Ice melts because of atmospheric warming. Australia reorganizes because the southern annular mode shifts under greenhouse forcing and ozone effects. These explanations are true. The framework of the hidden axis does not replace them. It sits beneath them. Conventional explanations describe what happens at Earth's surface. They share an assumption: the surface is the stable reference frame. Poles move relative to the surface. Ice melts on the surface. Weather operates above the surface. The crust is treated as the fixed canvas on which planetary events are painted. But what if the surface is not the most stable thing in the system? In 1905, Albert Einstein changed how physics understood motion by showing that observations depend on the reference frame from which they are made. A person on a train and a person watching from the platform describe the same event differently, and both descriptions can be correct within their frames. Geophysicists measure magnetic pole movement against latitude and longitude on Earth's crust. When they say the north magnetic pole moved 2,200 kilometers, they mean it moved relative to that surface grid. But the magnetic field is generated 2,900 kilometers below the surface, in liquid metal that has its own dynamics and angular velocity. The sun does not interact with a latitude grid. The solar wind encounters the magnetic structure generated in Earth's core. The book therefore proposes a more fundamental reference frame: the magnetic axis, the line joining the magnetic poles through the center of Earth. From that frame, the question inverts. Not, where is the magnetic pole moving across the surface? But, where is the surface moving relative to the magnetic axis? That inversion is the conceptual foundation of the deeper framework. The idea that Earth's surface can migrate relative to its deeper interior is not speculative. Geophysics calls it true polar wander. True polar wander, or TPW, describes rotation of Earth's solid outer layers, the lithosphere and upper mantle, relative to the spin axis and deeper interior. Like any rotating body, Earth tends to orient so its spin axis passes through its maximum moment of inertia, the direction where mass is most concentrated. When mass is redistributed through growing or melting ice sheets, mountain building, or movement in the mantle, the outer planet readjusts toward a new equilibrium. Picture a raw egg spinning on a table. If the denser yolk shifts, the egg wobbles and reorients because its mass has moved relative to the spin axis. Earth responds on geological scales. Continents, ice sheets, mountains, and ocean basins alter the planet's mass distribution. When that distribution changes, the outer shell reorients. Paleomagnetic signatures frozen into ancient rocks preserve the direction of the field when those rocks formed. By reading those natural compasses across continents and ages, geophysicists reconstruct the surface's position relative to the spin axis over billions of years. The record shows repeated, significant movement. The manuscript describes an Ediacaran event about 800 million years ago in which Earth's outer layers may have rotated by as much as 50 degrees. Smaller events appear in the Cretaceous and Cenozoic records. Satellite measurements show that polar drift continues today. The book cites research finding that its direction shifted around the year 2000 and proposing accelerated ice melt, especially in Greenland and West Antarctica, as the primary driver. True polar wander is confirmed science. Ice mass redistribution can drive surface migration relative to the rotation axis. The hidden axis extends that principle into the electromagnetic domain. Just as the surface migrates relative to the spin axis, the framework proposes that it migrates relative to the magnetic axis, and that atmospheric organizing systems respond to that changing relationship. The magnetic axis originates in the geodynamo, operating from 2,900 to 5,150 kilometers beneath the surface. Earth's liquid outer core is approximately 2,200 kilometers thick. Temperatures range from roughly 4,000 degrees Celsius at its outer boundary to about 6,000 degrees near the inner core. The metal is about 11 times denser than water and is in constant turbulent motion, driven by heat and organized by planetary rotation. Moving conductive liquid generates electrical currents. Those currents generate a magnetic field. The existing field helps sustain the currents that regenerate it. This self-sustaining geodynamo has operated, through interruptions and reversals, for about 3.5 billion years. The instantaneous field is complex, lobes, reversed flux patches, and secular variations evolving over years to millennia. Yet across tens of thousands of years, its dominant form is a geocentric axial dipole, organized mainly along the rotation axis with the magnetic poles averaging near the geographic poles. The long-term alignment is not accidental. Rotation and the Coriolis effect organize convection in ways that favor an axial dipole. The magnetic axis is coupled to the rotation axis by rotating fluid dynamics. The rotation axis, in turn, is coupled to the solar system's angular momentum. For the framework, this means the magnetic axis wanders in the short term but remains constrained over the longer cycles relevant to grand solar minimums. It is not absolutely fixed. Poles wander. Excursions occur. Reversals happen. But the book argues it is stable enough relative to the Sun for surface migration around that framework to have measurable atmospheric consequences. The surface is not a stationary stage. The outer core is not a silent background. Between them is a moving relationship, and above them is the solar environment that meets the field before it meets the world where people live. The next link is electromagnetic coupling, how energy from the Sun enters the magnetic system and reaches the atmosphere. The solar wind carries more than particles. Embedded within it is the interplanetary magnetic field, or IMF, continuously interacting with Earth's magnetosphere. When the interplanetary field is oriented opposite to Earth's field at the magnetopause, magnetic reconnection can occur. Field lines break and reconnect across the boundary, allowing solar wind energy, particles, and magnetic flux to enter the magnetosphere. Reconnection is the primary pathway by which solar wind energy reaches Earth's upper atmosphere. It drives auroral currents, heats the polar thermosphere, and moves plasma through the magnetosphere. Solar flares, coronal mass ejections, and ordinary variations in solar wind become part of Earth's electromagnetic environment through this process. The geometry of reconnection depends on the orientation and configuration of Earth's field. As the magnetic poles move and field geometry changes, the book argues that the pattern of energy deposition changes with it. The auroral ovals are the visible expression, rings of electromagnetic activity centered on the magnetic poles. As the poles move, the ovals move. Regions receiving maximum upper atmosphere energy input shift as well. The least understood link is the passage from ionosphere to troposphere, the lower atmosphere where weather occurs. The manuscript identifies electric field coupling, particle precipitation that changes atmospheric chemistry, and thermal effects from auroral heating propagating downward through the stratosphere. It states that the magnitude relative to ordinary thermal forcing is debated, while maintaining that the physical coupling exists. The framework's mechanism is precise. Pole movement shifts the electromagnetic framework of the upper atmosphere. Energy deposition patterns shift. Circulation organized partly around that framework changes its longitude of expression. During grand solar minimum conditions, weakened solar electromagnetic coupling amplifies coherence loss in zones corresponding to the pole's new position. The chain is complex and partly understood, but the book presents every link as physical: solar wind to magnetosphere, magnetosphere to ionosphere, ionosphere to atmosphere, and atmosphere to the geographic pattern of disruption. The Sun's 11-year activity cycle is the carrier wave. Longer cycles modulate its amplitude and determine how deep and sustained periods of reduced solar activity become. The approximately 208-year de Vries, or Seuss, cycle is the book's primary historical climate signal. When several consecutive 11-year minima become unusually deep, the result is a grand solar minimum lasting decades or nearly a century. The manuscript identifies 4 such minima in the past 6 centuries, the Wolf minimum from roughly 1280 to 1350, the Sporer from 1420 to 1570, the Maunder from 1645 to 1715, and the Dalton from 1790 to 1830. Each was associated with cooling and agricultural stress. Each occurred with the North Magnetic Pole in the Canadian Arctic. Each struck the same radius zones. The approximately 1,000-year eddy cycle modulates how deep de Vries troughs become. The medieval warm period occurred near an eddy maximum. The Little Ice Age unfolded as the cycle descended, providing a background in which the Maunder and Dalton minimums became severe. The approximately 2,500-year Hallstatt cycle modulates the eddy scale. The book places the present in a declining Hallstatt phase, with the eddy cycle beginning descent and the de Vries cycle approaching a trough. No one cycle is at its most extreme. The framework identifies their shared direction, combined with the pole's Russian Arctic position and a weakening magnetic field, as a convergence of planetary stress factors. This leads to the radius model. If electromagnetic organization is disrupted around the pole during solar minimum conditions, consequences should be strongest nearest the pole and grade outward with distance. Historical minimum period effects followed radius zones centered on the Canadian Arctic pole. But the pole has moved 2,200 kilometers. The radius has rotated. The model is dynamic, not permanent. Its geographic prediction depends on the pole's position during a specific minimum. History shows what happened under the old geometry. The physics of the current pole position determines where the book expects the next concentrated stress. In 1920, Serbian engineer Milutin Milankovic worked in a Budapest library while interned during the First World War. His problem was immense: calculate how solar energy reaching every latitude changes across thousands of years as Earth's orbital geometry slowly varies. He combined 3 cycles: the shape of the orbit, the tilt of the axis, and the wobble of that axis, into curves of insolation across past and future time. He worked without computers. Decades later, ice cores showed that glacial cycles followed the orbital schedule he had calculated. The Epica Dome Sea project drilled 3,270 meters into Antarctic ice and recovered about 800,000 years of continuous climate history, 8 complete glacial interglacial cycles. The first orbital cycle is eccentricity, the changing shape of Earth's orbit. It operates principally near 100,000 and 413,000 years. Earth's current eccentricity is about 0.017, in the lower third of its range. Direct annual energy change is small, about 0.1%, but eccentricity amplifies or mutes precession by changing the difference between perihelion and aphelion. The second is obliquity, Earth's axial tilt. It varies from approximately 22.1 to 24.5 degrees over 41,000 years. The current tilt is about 23.4 degrees and decreasing. Greater tilt intensifies high-latitude seasons. Smaller tilt cools polar summers and favors survival of winter snow. The third is precession, the roughly 26,000-year wobble of Earth's axis. Polaris is not always the North Star. The axis once pointed toward Thuban and will point toward Vega again. Precession advances about 1 degree every 72 years and determines which season occurs closest to the Sun. Together these form the sky's long clock. They govern the distribution of solar energy across latitude and season, and they pace the advance and retreat of ice over hundreds of thousands of years. But the ice record revealed a problem Milankovic's basic calculation could not completely solve. The 100,000-year problem is the central puzzle in Milankovic cycle science. It has 3 parts. First is magnitude. Eccentricity causes the smallest change in total annual solar energy, about 0.1%, while obliquity and precession create larger changes in energy distribution by latitude and season. Yet for the past 800,000 years, ice ages have followed the weaker 100,000-year eccentricity rhythm. Second is timing. Deglaciations happen rapidly. The transition from maximum ice to minimum ice can occur in roughly 10,000 years, much faster than a gradual orbital change alone appears to imply. Something amplifies the orbital signal at termination boundaries. Third is asymmetry. Ice ages build slowly across tens of thousands of years, then end abruptly. The orbital forcing rises and falls more symmetrically than the climate response. The system enters glaciation slowly and exits quickly. Ice albedo feedbacks, carbon cycle changes, and ocean circulation are real mechanisms invoked to explain the pattern. The hidden axis proposes that geomagnetic behavior is an additional missing element. For magnitude, it proposes that eccentricity modulates cosmic ray variation, while geomagnetic strength controls how much of that variation reaches the atmosphere and affects clouds and chemistry. For timing, it proposes that geomagnetic excursions and intensity shifts can rapidly reorganize the atmosphere near termination boundaries. For asymmetry, it proposes a nonlinear feedback between field behavior and the loading or unloading of ice sheets. The manuscript labels these as framework inferences requiring systematic tests against paleomagnetic and paleoclimate records. It identifies the mid-Pleistocene transition, when glacial pacing shifted from approximately 41,000 to 100,000 years, as a possible threshold in the field's long-term evolution. Before that transition, the field configuration may have amplified obliquity. Afterward, it may have amplified the eccentricity-precession interaction. The hypothesis is bold because it offers one connected explanation for magnitude, timing, and asymmetry. Its proposed physical bridge is the cosmic ray connection. Cosmic rays are high-energy particles, primarily protons and atomic nuclei, produced by supernovae, neutron stars, and other energetic processes across the galaxy. They arrive at Earth from every direction. The geomagnetic field deflects many of them, especially at low latitudes where the shielding is strongest. Near the poles, converging field lines allow more particles into the atmosphere. When cosmic rays penetrate the lower atmosphere, they ionize molecules. The resulting charged particles can participate in the formation of aerosols and condensation nuclei for water droplets. The Svensmark hypothesis proposes that changes in cosmic rays significantly influence low-level cloud formation and therefore surface temperature. The manuscript notes that the magnitude is debated while presenting ionization, aerosol formation, and cloud development as the physical pathway. The hidden axis connects this pathway to eccentricity. When Earth's orbit is more elliptical, the contrast between perihelion and aphelion becomes larger. The book proposes that this produces greater annual variation in solar wind shielding and, in turn, greater variation in galactic cosmic rays reaching Earth. Earth's magnetic field is the second gate. When it is strong, it deflects more cosmic rays despite variations in the solar wind. When it weakens, more penetrate to lower altitudes, and the orbital variation can exert a larger atmospheric effect. The proposed mechanism is therefore an interaction. Eccentricity modulates cosmic ray variation, solar activity modulates entry into the inner solar system, geomagnetic strength modulates entry into Earth's atmosphere, ionization influences aerosols and clouds alter reflected sunlight. In the framework, the 100,000-year eccentricity cycle dominates when geomagnetic strength falls within a range that amplifies this cosmic ray signal. The 41,000-year obliquity rhythm dominates under another magnetic configuration. This chain requires empirical confirmation at every link. But the book identifies an event in the geological record that shows what can happen when Earth's magnetic shield is severely weakened. It happened 42,000 years ago. 42,000 years ago, during the Lost Champ excursion, Earth's magnetic field weakened to approximately 10% of its current strength. The poles wandered toward middle latitudes, and the magnetospheric shield was reduced to a fraction of its normal capacity. The excursion lasted several thousand years. At its peak, the book states that cosmic ray flux in the lower atmosphere approximately doubled. Carbon-14 and beryllium-10 production spiked, leaving synchronized signatures in ice, sediment, and tree rings. The manuscript presents three categories of consequence. In biology, Australian megafauna extinctions cluster in the Lost Champ period, while European Neanderthals entered their final decline. It presents increased ultraviolet exposure, disrupted food webs, and changing plant distributions as possible added pressures. In the atmosphere, synchronized records show disruption in both hemispheres, including Australian aridity and changes in Southern Ocean wind and current patterns. Ozone disruption and increased ultraviolet radiation altered surface conditions and lower atmosphere chemistry. In culture, the expansion of European cave art at sites including Chauvet, Lascaux, and Altamira begins during the same broad period. The book recounts the proposal that shelter from increased ultraviolet radiation may have placed more people in caves, contributing to the conditions in which cave art flourished. The hidden axis does not predict a new Lost Champ event in the coming decades. It states that the current field, about 15% below its 1840 measurement, is nowhere near Lost Champ magnitude. Lost Champ serves as an existence proof that severe geomagnetic weakening can accompany global atmospheric and biological consequences. The current picture is convergence without equivalence, relatively low eccentricity, decreasing obliquity, precession moving toward less northern summer energy, a weakening geomagnetic field, and de Vries, Eddy, and Hallstatt cycles all moving toward reduced solar activity. None is at its greatest extreme. The book argues that their simultaneous direction creates a compound stressor, not imminent glaciation, but geographically concentrated atmospheric stress operating against the powerful counterforce of modern greenhouse warming. Below that atmosphere, the geological system is already responding. On the night of November 9, 2021, a fissure opened on Iceland's Reykjanes Peninsula and lava reached the surface in a zone that had been quiet for roughly 800 years. There was no towering ash cloud. People walked close enough to feel the heat of new rock forming. Scientists placed instruments near the flow. Beneath the spectacle was the greater fact: the last eruptive period in this zone ended around 1240. Then came eruptions in 2021, 2022, 2023, and 2024. Grindavik was evacuated repeatedly as lava threatened roads, homes, and commercial structures. Iceland sits where the North American and Eurasian plates pull apart, above a mantle plume. The peninsula was never geologically dead. But the manuscript identifies accelerated crustal uplift, linked to loss of ice from Vatnajökull, as part of the changing pressure environment beneath the island. Ice is geology. 1 cubic meter weighs about 917 kilograms. A column 1 kilometer high exerts roughly 9 megapascals of pressure at its base, around 90 times atmospheric pressure. Greenland's ice reaches about 3,200 meters thick and depresses the bedrock beneath it by hundreds of meters. Remove ice and the land rises through isostatic rebound. In most regions, the mantle responds across thousands of years. Scandinavia and northern Canada are still rising from ice lost at the end of the last glacial period. Ancient shorelines in Scotland now stand above the sea. Iceland and West Antarctica respond much faster because the mantle beneath them is unusually hot and fluid. The manuscript cites uplift around 20 mm per year in active Icelandic zones and 40 to 50 mm per year in West Antarctica. Iceland makes the geological cascade visible. Atmospheric change redistributes ice. Ice loss unloads the crust. Rebound changes the pressure surrounding magma. The probability of eruptions rises. The ice moves. The crust responds. The magma stirs. The geological cascade has 4 links. Link 1, atmospheric reorganization changes precipitation. Storm tracks shift. Some regions receive more moisture, others receive less. Snow accumulation and melt change geographically. Link 2, redistributed ice changes the load on the crust. Land beneath lost ice rebounds. Land beneath growing ice subsides. Faults and magma chambers enter a new mechanical environment. Link 3, pressure changes affect volcanic and seismic systems. Reduced confining pressure allows dissolved gases to leave magma more easily, increasing buoyancy and mobility. Differential rebound changes stress along faults. Beneath marine ice, unloading affects submarine bedrock and volcanic systems. Link 4, eruptions return the cascade to the atmosphere. Sulfate aerosols injected into the stratosphere reflect incoming sunlight and temporarily cool the lower atmosphere. Geological activity amplifies the atmospheric disruption that initiated the chain. The result is a feedback loop: atmosphere to ice, ice to crust, crust to volcano, volcano back to atmosphere. Because geology responds with delay, volcanic amplification can continue after the solar driver begins recovering. West Antarctica is the southern analog to Iceland. Its ice sheet holds about 2.2 million cubic kilometers of ice and loses approximately 138 gigatons per year. Beneath it lies a 3,000-kilometer rift system and a province where the manuscript cites 138 buried volcanic structures. It predicts elevated volcanic probability as continued ice loss lowers confining pressure, without predicting a specific eruption or date. The Ring of Fire is the more distant expression. It contains roughly 75% of the world's active and dormant volcanoes and about 90% of its earthquakes. Tectonic forces remain primary. The framework adds a statistical prediction: mass redistributed from land ice to the global ocean subtly changes stresses in already strained subduction zones, elevating volcanic and seismic activity during minimum periods. The prediction is not a calendar of disasters. It is a testable increase in frequency across the system. History, the book argues, shows the geological cascade operating during grand solar minimums. The Maunder minimum began around 1645. As solar activity remained suppressed, the Little Ice Age intensified, the Thames froze, and alpine glaciers advanced. Major eruptions clustered through the following decades: Parker Peak in the Philippines, Hokkaido Komigatake in Japan, Sheveluk in Kamchatka, and repeated activity at Iceland's Grimsvatn beneath the Vatnajökull ice cap. The conventional reading treats eruptions as independent events that added cooling. The framework reverses the upstream causation: minimum period atmospheric reorganization redistributed ice, changing ice loads altered crustal stress, volcanic probability rose, volcanic aerosols then amplified the cooling. The Dalton minimum provides the book's clearest example. It began near 1790. 25 years later, Tambora produced the largest eruption in recorded history. The following year, 1816, became the year without a summer and one of the most severe agricultural crises in recorded Europe and North America. The hidden axis reframes the sequence. Tambora did not independently create the entire crisis. It amplified minimum period atmospheric disruption already underway, while the preceding decades of altered climate and ice distribution formed part of the geological cascade that the framework proposes helped prime the eruption. Today, that cascade is presented as present tense. Iceland has entered repeated eruption after centuries of surface quiet. West Antarctic bedrock is rising rapidly beneath a thinning ice sheet and a major volcanic province. The Ring of Fire prediction will be tested as the solar minimum period develops. The framework does not name the date of a specific eruption. It predicts elevated geological activity during the minimum relative to surrounding solar maxima. The planetary mechanism is now in place: moving reference frames, a core-generated magnetic axis, solar electromagnetic coupling, nested solar clocks, orbital cycles, cosmic rays, ice redistribution, crustal rebound, and volcanic feedback. The ice moves. The crust responds. The magma stirs. The volcanoes wake. It has operated before. Episode 3 enters the historical proof.